Just asked an AI to plan a trip that I'm probably not gonna take. But you know, what still gets me is how fast that became normal. You just have a question, you type it, you get an answer. Easy, right? No more search, no more tabs, no more 20 minutes of figuring out which source to trust. It just works. And you stop thinking about how. But what I find more interesting is what underneath all of it. I mean, not the intelligence part, the physical part. The stuff you don't see when you're typing into a chat window. This is what this video is about. Artificial intelligence is being used to predict floods. It is helping to optimize power grids, reduce industrial emissions, and cut response times in supply chains. It is among the most computationally intensive technologies ever deployed. But, you know, the physical world has just other plans. Somewhere in Tennessee, a utility company is on the phone. The engineer on the line is not calling a technology supplier, he's not calling a grid operator. He is calling other utility companies in the Tennessee Valley, one by one, asking if they have spare transformers they can track in. Why? Because a new AI data center needs a grid access, and the grid cannot keep up. The same shortage stopped something else. A housing project for at-risk young adults sat idle. The grid connection was delayed. The transformers were not available. The most advanced computing in the world runs on 19th century hardware, and there is not enough of it to go around. There are 6,111 data centers in operation worldwide. Each one requires a connection to the electrical grid. Each grid connection requires a large power transformer. And the current wait time for a large power transformer is 3 to 5 years. And that was before tariffs. Crazy, isn't it? To understand how we got here, you have to understand what AI actually is. I mean, not the model, the machine. The cloud actually has an address, and it's not where you think. The accepted story goes like this. AI is a software revolution. It lives in the cloud. The cloud is clean, efficient, and carbon neutral. The companies building it have pledged 100% renewable energy. They are using AI itself to optimize power grids, shift computing loads to cleaner regions, and reduce the emissions of industries they serve. The numbers appear to support this. 6,111 data centers, matching 100% of electricity consumption with renewable energy purchases. Google has a carbon intelligent computing platform. It shifts workloads globally in real time to match local grid carbon intensity. That is a coherent story. It is a story the industry tells. It is the story in the annual reports. But it is also incomplete. 6,111 data centers means 6,111 physical buildings. 6,111 connections to a physical grid. 6,111 sites that need water, power, and cooling every hour of every day. Turns out the cloud has weight. It has a water bill. It has a transformer on a loading dock somewhere waiting. Every one of those 6,111 facilities runs on 3 physical inputs: water, electricity, and cooling. And right now, all 3 are under pressure. Here is what the annual reports do not show you. Phoenix, Arizona, a desert city, low humidity, cheap electricity, aggressive tax incentives, and low neutral disaster risk. Tech companies chose Phoenix for exactly those reasons. They didn't choose it for its water. The average hyperscale data center in the United States consumes roughly 550,000 gallons of water per day. A mid-sized facility uses 370,000 gallons per day. That water comes from the same municipal supply that Phoenix residents depend on. Phoenix's 2021 water resource plan didn't account for data centers. The facilities were not in the projections. Meanwhile, globally, the demand for fresh water is expected to outstrip the supply by 40% before the end of this decade. That's insane. Now move east to Memphis, Tennessee. A utility company is trying to connect a new AI data center to the grid. The connection requires a large power transformer. The transformer has a delivery window of 3 to 5 years. The core technology inside that transformer hasn't changed in over 100 years. Transformer prices have nearly doubled since 2018. Then tariffs on steel drove a further 20% price increase almost immediately. In the United States alone, there are 80,000 varieties of small electrical transformers. Each is custom to its application. That variation makes standardization difficult and supply chains slow to scale. And yet, transformer manufacturers are not building new factories. After 2008, they expanded production to meet a surge in infrastructure spending. The surge ended. They were left holding factories they could not fill. They will not expand again on the strength of a boom they do not trust. In shortage, projects with the deeper pockets gain leverage. Utility companies find themselves at the back of the queue. Municipal grid upgrades wait. Renewable energy installations wait. Housing projects wait. Marty Ivy, General Superintendent at Mayfield Electric and Water Systems, said, "We have begged, borrowed, and pleaded with other utilities in the Tennessee Valley to get transformers. Water and power are two constraints. The third is physics. Modern AI and high-performance computing chips generate heat at densities about 100 watts per square centimeter. That exceeds where air can physically remove." So 3 separate constraints: water, power, heat, each one verified. You do not have to take a journalist's word for it. The companies put it in writing themselves. In 2024, Google published its environmental report. It's a public document, audited, signed, submitted. It shows that Google's total greenhouse gas emission increased by 13% year over year in 2023. The primary driver? Data center energy consumption. The same report states that Google matches 100% of its electricity with renewable energy purchases. And both statements are true. Together they describe something the industry rarely explains. Matching 100% of electricity volume with renewable purchases doesn't mean the electrons powering the servers are renewable. It means that somewhere Google paid for an equivalent amount of renewable electricity to be generated. The actual electrons running through the cables come from whatever the local grid is producing at the moment. Geographic and timing constraints mean fossil fuels fill the gaps. Google's Scope 2 market-based emission rose. Even under the accounting most favorable to the company's claims, emissions went up. The industry measures efficiency with a metric called power usage effectiveness. It compares the total energy a data center uses to the energy delivered to the IT equipment itself. The industry points to low PUE scores as proof of efficiency. Power usage effectiveness does not measure efficiency of computing hardware. It measures facility overhead. A facility can score well on the PUE while running hardware which is highly energy intensive. The metric measures the building, not the machine. Vertiv Holdings is a primary digital infrastructure provider. Its SEC filings are legally binding disclosures. Vertiv's filings state that the company is heavily expanding its thermal management portfolio, specifically to handle the complexity created by hybrid air and liquid cooling in AI data centers. Trane Technologies raised its 2024 revenue forecast by 11%.
The driver is commercial demand for heating and cooling systems tied up to the AI boom.
These are not analyst projections. They are earnings goals, environmental reports, SEC filings. The companies growing fastest from AI are the ones managing heat and power, not the ones building models. So information was never hidden. It was disclosed, footnoted. It was available to anyone who looked.
Here's why this does not self-correct. The industry has a solution: liquid cooling. Run fluid directly to the chip, remove the heat before it accumulates. It works. There is a problem with the most effective version of that solution. The most capable cooling fluids for high-density AI chips are dielectric fluids, substances that conduct heat but not electricity, allowing direct contact with live hardware. Among the most effective are PFAS compounds, which are perfluoroalkyl and polyfluoroalkyl substances. They are known as forever chemicals. They persist in soil, in water, and in living organisms. Regulators across the world are phasing them out because of environmental persistence and toxicity concerns. 3M manufactured a dielectric fluid called Novec. It was among the most effective fluids available for immersion cooling. 3M exited Novec manufacturing in 2025, forced out by environmental regulations. Some of the most effective fluids for immersion cooling are being removed from the market at the same time demand for liquid cooling is rising.
Legacy data centers were built for air cooling, so switching to liquid means rebuilding from inside out. New pipes, new equipment, new floor architecture. Most operators actually just cannot absorb that kind of cost quickly. And yet, 88% of data center cooling revenue still flow to legacy air-based systems. Not because air cooling works well for high-density AI. For modern chips, it does not. But because the cost of changing is higher than the cost of managing a system that is already under strain. Interesting, isn't it? The industry knows what needs to change, it just cannot afford to. Let's return to the transformer. Every market signal says build more capacity. But the transformer manufacturers are not building more capacity. They just remember what happened last time. And I mean, who could blame them? The system is not broken. The manufacturers are making a rational decision. The memory of the last time they responded to a boom is stronger than the signal to expand. Chips produce more heat than air can remove, so the industry needs liquid cooling. Some of the most effective cooling fluids are being banned, so the industry needs alternatives. Those alternatives require water infrastructure, which strains municipalities already running short. Meanwhile, the facilities need grid connections, and transformers take years to arrive. The manufacturers will not scale up because the last boom ended badly. Each solution creates the next constraint. The bottleneck is not one thing, it is the system of interlocking problems, each one rational on its own. That is what makes this structural, not cyclical. There are paths forward. Engineers are working on them, and of course some companies are ahead. But the gap between what AI requires and what physical infrastructure currently provides remains wide. And that gap is the story. The path forward is not a mystery. Two shifts, both difficult. The hyperscalers building the largest clusters are already deploying liquid cooling. The rest of the industry is watching the capital cost and waiting. Microsoft has piloted zero water cooling designs. Still pilots, not yet at scale. A pilot and a deployed system are not the same thing. Most of the industry currently lives in that gap. The second shift is less obvious. Liquid cooling exhaust exits facilities at up to 55 degrees Celsius, warm enough to heat buildings, greenhouses, or industrial processes currently running on fossil fuels. The district heating model would convert that waste into a resource. But most desert facilities were not built near the infrastructure they would need to serve.
Neither of these shifts remove the underlying constraints. They work within them. The semiconductor factories that manufacture AI chips are highly water intensive. An average factory uses as much water as 33,000 American homes. That is before it ships a single chip. Go back to the beginning. A utility engineer in Tennessee is on the phone. He's calling other utilities one by one, asking if they have a spare transformer. Not because someone failed to plan, because a housing project is waiting, because the grid cannot keep up, because the most powerful computing technology ever deployed draws its power through a metal box that has not changed in 120 years. Somewhere in Arizona, a data center is pulling 550,000 gallons of municipal water supply that was not built to support it. The city's 2021 water plan did not see it coming. The desert was chosen for its dry air. Nobody planned on the water bill. And in rack somewhere inside that facility, a chip is running at over 100 watts per square centimeter. The fan is spinning about it. The fan is losing. And this is the physical cost of the intelligence we're building. Not invisible, not weightless, not clean. Iron, water, and heat. The cloud always had weight. We just stopped looking for it. Thank you so much for watching this video. If you have any questions, feel free to ask them in the comments. I'll be happy to answer. And like and subscribe if you want to see more content like that, and see you in the next videos.